So now we're going to talk about chemical reactions and classifying chemical reactions into categories, because all reactions have a heading that they go under. We're going to talk about a few major categories that we're going to use when we talk about different types of chemical reactions. This goes back to our main focus for this part of the unit, that all chemical reactions can be represented by balanced chemical equations. And now we've been looking at how to balance them, and now we're going to look at how to identify the type of reaction that you're looking at. We'll go through the four main types of reactions and talk about how you can identify the type of reaction by looking at a balanced equation. These are the four major types. There are a couple of other sort of subcategories, one of which we'll talk about, one of which we'll mention briefly. But synthesis, decomposition, replacement, and combustion. Replacement is also sometimes referred to as displacement reaction, but they're interchangeable, displacement or replacement. So a synthesis reaction, right? Synthesis means putting together, right? If you synthesize ideas in an essay, or you use a synthesizer, it puts together different sounds, a musical instrument. So a synthesis reaction is a reaction that combines elements or compounds. And there are lots of reactions that do this, but specifically a synthesis reaction is one where you have at least two reactants, but you only have a single product. Okay? Now, A and B could both be elements, or they could be compounds, or they could be any sort of combination of those two things. So A might be an element and B might be a compound, or vice versa, or they both might be elements, or they both might be compounds. That's not really the key. The key to identifying a synthesis reaction is that there is only a single product. Okay, that's the key. Here's an example. Right? In this case, A and B are both compounds. A is calcium oxide, B is water, and when you combine them, you get calcium hydroxide. Now, they're not exactly in the same order that they were, but you can see that there's a calcium, two oxygens, and two hydrogens. A calcium, two oxygens, and two hydrogens. So it's all the same atoms. They've just been combined from these two compounds to form a single product, okay, calcium hydroxide. Here's another example. In this case, A and B are both elements, right? A would be magnesium, B would be oxygen, and those two combine to form the single compound magnesium oxide. So that's another example where A and B are elements, and the last one we had A and B both compounds. Or you could have one element and one compound. But in both cases, the product is a single compound. A decomposition reaction is the reverse. Right? In a decomposition reaction, you have one reactant that then breaks apart to form two or more. In both of these cases, the synthesis might have more than two reactants. The decomposition could have more than two products, but this is just showing you this example. And again, A and B could be elements or compounds, but the key is, in a decomposition, there is only a single compound as a reactant that's then broken down. In an example here, we have hydrogen peroxide, H2O2, and that breaks down into the compound water and the element oxygen. So the AB would be the peroxide, the A in this case would be the water, and the B would be the oxygen. So we have a single compound breaking down into two products. One's a compound, one's an element. And then replacement reactions, and there's two types, but they both fall into this same broad definition in which you have certain elements trading places and generating new compounds. So that's the basic distinguishing characteristic of a replacement or displacement reaction. In single replacement, you have, in this case, A has to be an element. Okay, A cannot be a compound. And on the other side, B is a single element. And then, obviously, on the reactant side, B is combined with C to form a compound. And on the product side, A is bonded with C to form a compound. So here's how it works, right? You've got A replacing or displacing B, so that as a product, you have B by itself as an element, and A has now become part of the compound. So the element that starts out by itself becomes part of the compound, and the element that was in the compound is now by itself. Okay, so that's the key hallmark of a single replacement reaction. So here's a typical example. All right, if I have silver nitrate, and this would generally take place in a solution where you've dissolved the silver nitrate and then you add copper. So the element A is copper, B is the silver, C is the nitrate. So C could be a polyatomic ion or another element. The copper replaces the silver and leaves the silver as an element by itself. Now the copper has become part of the compound as a product, so the copper replaces the silver. So the element that starts out by itself is now in the compound over here, and the element that was in the compound is now by itself. So they've traded places. How do we know which elements are more reactive? Because it's the more reactive elements that displace the less reactive elements. We have this thing called an activity series, which we'll take a look at another time. But it has the most reactive elements at the top and the least at the bottom. And then there's a whole list of elements in between. And basically the way you look at it is you would look at, the copper and the silver, for example, in that last equation. And if copper is closer to the top, to the most reactive elements, so if copper is here and silver is somewhere down below, that means that copper is more reactive than silver, so copper can displace or replace the silver atoms. If it was the other way around, if the silver was by itself, and then if we have the nitrate, right, the compound, and then it was copper nitrate, well, since, as it says down here, since the more reactive element is already in the compound, silver is not reactive enough to displace copper. So if this was the case, you would actually have no reaction at all because the silver can't overcome or displace the copper. Okay, so then a double replacement. So we had single displacement or single replacement. Now a double replacement. Okay, one of the key factors here is that you have 4 substances, 2 reactants, 2 products, both compounds, right? So in the single displacement, you had an element in a compound. In a double replacement, you have 2 compounds on both sides. And what's really happening here is the compounds are essentially trading partners, right? So the C goes to the B, and the A goes over to the D, right? So you're just sort of rotating the parts. And it always has to be, depending on how you want to write it, it's either the first half switches with the other first half, or you could have the B and the D trade places, but you can't have the A and the C go together and the B and the D. Because normally we're talking about ionic compounds here, and if you try to put the A and the the A and the C together, those are both metals and they won't bond because they're both positive ions. So whichever way you want to do it, you can have the A and the C trade places, or you could have the B and the D trade places, but you can't put the A and the C together in this scenario. So I'll show you what I mean on the next slide in the example. So here's calcium hydroxide and hydrochloric acid. So this is actually an example not only of a double replacement reaction, but also of an acid-base reaction. Okay, and how do you know if it's an acid-base reaction? Well, you've got one compound that has OH in it, and that would be at the end, and the other compound has the H at the beginning. So what's going to happen is when in this case it was the B, the B and the D that traded places. So the chlorine swaps places with the hydroxide. So over here you have calcium chloride, right, because the chlorine came over, and this is the hydrogen and the hydroxide, HOH or H2O, right? So the water. So whenever you have an OH and an acid, a base and an acid, you end up with one of the products being water, because when the hydrogen bonds with the hydroxide, it's two hydrogens and an oxygen, so that's water. So this is an example of both. So it's a double replacement reaction. That's the main type. Specifically, this type of double replacement reaction is called an acid-base reaction, just because of the OH here and the H. We haven't talked a lot about acids and bases yet, but we're going to talk more about them later. So that's where you had two compounds on the left and two compounds on the right, and the difference from left to right is that the compounds traded partners. That's a double replacement, and that one happens to be acid-base. All right, so in a double replacement reaction, again, you're usually talking about substances that have been dissolved in water and make solutions, and then you mix the solutions together, and now all the things that are dissolved kind of start mixing around and bumping into each other, and they form new combinations than what they had before. And what they had before, if it was in a solution, dissolved in water, which is called soluble. And sometimes when you get those new combinations, one of the combinations becomes insoluble and no longer will dissolve in the water. And so it goes from being dissolved to being a solid. That solid is called a precipitate. So a precipitation reaction is one where you mix two solutions and the new combination produces something insoluble, the precipitate, and it precipitates out, just like we have precipitation that's rain or snow coming out of the air. So a precipitate is one possible product of a double replacement reaction. The other two possibilities are a gas, so bubbles, right? Or, as we just saw in the acid-base reaction, sometimes one of the products is water. Double replacements always produce one of these three things. Precipitate, which is a solid, a gas, which you'd see in the form of bubbles, or water. The problem with water, of course, is if you're mixing two beakers filled with water, with stuff dissolved in them, and they turn into water, you can't really see, there's no real visible evidence, right? It's not like there's suddenly more water or less water that you'd notice. So you'd have to look for another way to identify whether there was a reaction there. Okay, the last type of reaction we're going to talk about is combustion. And the key here for combustion reactions is oxygen is one of the reactants. And really, it should be O2, right? Because oxygen is a type of element that always forms pairs when it's existing as an element. And then I would need an O2 over here. So the key factor in combustion is O2 is one of the reactants. O2 is one of the things on the left, and it's just O2 by itself. It's not like CO2, right? That's not oxygen, that's carbon dioxide. So that doesn't count. It's only when oxygen is as an element that we would call it combustion. So here's an example. All right, magnesium. Okay, so that's the A could be an element or a compound. The O is always oxygen. So there's your key factor that tells you this is a combustion reaction. And they combine to form magnesium oxide. Now, a little while back, on one of the earlier slides, I said that magnesium combining with oxygen, two reactants, one product, magnesium oxide, is synthesis, because you have a single product. That is true. Okay, you do have some reactions that fit into more than one category. This is both combustion and synthesis. Okay, because it's an element combining with oxygen, and they yield a single product. So it's combustion and synthesis. Either one is correct. Excuse me. If you were asked to identify the type of reaction, you would be most correct if you said both. Okay, but either one would be acceptable. So that's a combustion reaction that is a synthesis reaction, but there are plenty of combustion reactions that aren't synthesis reactions. So here's an example, and this is a very typical thing. This is propane. There's lots of these carbon-hydrogen compounds that bond with oxygen, and you get two products, carbon dioxide and water. So since there are two products, it's not synthesis, right? Can't be synthesis if it's got two products. So it's still combustion because of the oxygen, but it's not synthesis. So there are synthesis reactions that are not combustion reactions. There are combustion reactions that are not synthesis reactions, but there is overlap sometimes between those two types. When we think of combustion reactions, we often think of fire and explosions and heat and things like that that we can see and feel and that sort of thing, but they're not all the same, right? Respiration, when we take oxygen into our bodies and then use it for different things, that is very, very tiny, generally slow reactions that are still combustion reactions inside our bodies. Happen all the time. That's what makes our bodies work. So we're not generally bursting into flames or exploding, but we have combustion reactions going on inside our bodies all the time. And iron, or any metal, really rusting. So you put an iron bar out in the air and it slowly rusts. That iron is slowly burning. It's combusting. It's combining with the oxygen from the air to form a compound. So those are examples where we don't really have what we would consider flames and heat. When we do see flame, it's because atoms in the reaction are being excited by the energy that's generated, and that's what the heat is that we feel. And so the electrons take that energy and they jump up, right? We talked about excited electrons a while back. When they return to their normal state, they give off light. That's actually the color that we see when we see flame. All right, and then I believe this is the final one here. Not all explosions are the result of either a combustion typically, or it could be a decomposition reaction. What happens is you take either a solid or a liquid or a small amount of gas, and you have a reaction that generates more gas, right? More moles of gas. So solid converted to gas, or liquid converted to gas, or just a small amount of gas converted into more moles of gas. And because now suddenly you have more gas, the gas needs to take up more volume, because gases have a lot lower density than solids and liquids. So that gas wants to expand. It exerts pressure trying to get away, and that's what generates that shock wave that creates what we would call an explosion. Okay, so that's the reason that happens is because, for example, airbags in cars are inflated by a decomposition reaction. There's a little pellet of material inside the airbag, and when the car sensors detect what they think is a crash, they send a little electric spark into the pellet. The pellet decomposes, so the solid that's in there has a reaction that forms a gas. That gas expands and fills up the airbag, and that all happens in a couple of milliseconds. So explosions are the result of reactions that generate quantities of gas that exert pressure as they're trying to expand. Right? So those are the main types of reactions, and we're going to practice balancing equations and identifying the types of reactions. And then there's going to be a project, if you haven't already seen it, on creating a little booklet, sort of a brochure that explains a particular type. You can choose from one of the types that we just went over.